Hello everyone, Chicken Puck here. Today I'm going to prove that each subsystem of a singlet state has zero local spin expectation in every direction. So let's start with the actual problem. So this is the actual problem here. Given this singlet state here, we have two spin 1/2 particles A and B in the singlet state. The question is asking us, if we were to measure the expectation value of A by itself, will we get zero? If we were to measure the expectation value of B by itself, will we also get zero? Let's go through the actual notation. So before we jump in the problem, I want to go over some notation. As you can see, we have NA here, right? So what this is saying is this. A bit bigger. So what is this actually saying? So first of all, what is N? So when we say spin up, we don't mean in every direction, right? So we say spin up, we have to specify which direction we're actually using, which direction we're actually measuring spin along. So NA is simply the direction along which we're choosing to measure particle A. If we're measuring along the z-axis, we could then say z, A, right? So we could say z, or we could use x, right? We want this result to hold for any direction, so we call our arbitrary direction NA. This means spin up along the direction NA. So also needs to be true is that N has to be a unit vector. So why does N have to be a unit vector, right? Because we're using N to specify a direction, not a magnitude. If I were to write 0, 0, 1 and 0, 0, 5, these two vectors point in exactly the same direction. One is just 5 times longer. So making our arrow longer shouldn't change what direction we're measuring spin. So we normalize the N to length 1. So this is actually important mathematically because it gives our spin observable eigenvalues of exactly +1 and -1. So as you might know for an introductory quantum computing class, if I were to say this, so if we were to expand this out, we would get sigma n equals nx, sigma x plus ny, sigma y plus nz, sigma z, right? So what we're saying here is that sigma n is our spin observable along the direction n. These are the three Pauli matrices. So it's constructed using those Pauli matrices. And once we choose the direction n, this operator measures spin along that direction. Okay, now we're going to write the next step is summation NA of. So what does this mean? So the superscript A tells us that sigma acts on this subsystem A, and 1b is the identity operator on B. So the identity just leaves the B unchanged. So this entire expression just means measure the spin of A along NA while leaving B alone. So the 1 is acting on the A and measuring along the B. So why am I saying that the measurement gives +1 or -1? Why is that true for any direction n? Let's go over that. So if I were to say, so what is this saying? This is saying that we have lambda is the eigenvalue, which corresponds to a possible measurement result. So if I apply the operator again, let's say squared. But we know that this is equal to 1. So why is that equal to 1? Because n is a unit vector. The properties of the Pauli matrices say the properties of the Pauli matrices give us sigma n squared. That equals the identity, right? So we know this. So we know this has to be true. So therefore, what does that mean? Lambda squared equals 1. So because lambda squared equals 1, lambda equals what? It equals plus and -1, right? So the only two eigenvalues are +1 and -1. We call this the +1 eigenstate spin along n, and we call the -1 eigenstate spin down along n. So let's write this out a bit further, okay? As you can see here, I've written this, right? So the +1 here isn't arbitrary. It's the eigenvalue associated with the spin up along NA, and the -1 is the eigenvalue associated with the spin down along NA. So because n can point in any direction, this isn't limited to x, y, and z, right? So before we actually solve this, let's see if we can predict the answer. So for particle A in the singlet state, there's a 50% chance of getting +1 and half chance of getting -1, right? So imagine repeating that experiment 1,000 times, okay? So roughly 500 measurements give +1, then 500 give -1. So that would mean 1/2 +1 plus 1/2 of -1 equals 0, right? So the first 1/2 means how often we can expect +1. The second half means how often we can expect -1. So the positive and negative outcomes cancel on average. So more importantly, we never actually measure 0, right? So an individual measurement gives +1 or -1. 0 is the average we approach over many identically prepared experiments. So why are we going to take the expectation value? Let's see why. So as you recall, the expectation value. So this is why this problem is asking for this expectation value. In quantum mechanics, if O is an observable and the system is in state psi, this expression gives the expected average result of repeatedly measuring that observable on the identically prepared systems. This expression, going back here, this is really saying, if I repeatedly prepare the singlet state and measure only A along NA, what does the average result approach? So we think that's going to be 0. So let's prove it. So all I'm doing here is rewriting psi minus. So it's the same thing here, just written a bit bigger. We're going to apply this to our psi, okay? Put it out here. So as you can see, this is the original psi minus, and we applied the measurement on the A, leaving the B alone, and let's see what happened. This looks almost exactly the same, right? But if you notice, this minus has become a plus. And why is that? Because along this A, because the sigma is acting on particle A. So in our first term, A is spin up. So here, so the term stays the same. But in the second term, it's spin down. So spin down has the eigenvalue -1. So and remember, our singlet state already has a minus. So we have minus times minus equals +1. What happened here is psi minus becomes psi plus. Now let's calculate the expectation value. For simplicity, I'm gonna write down some simplified notation here. So let cat u equal A, B equal down. Now we can write so now we're going to perform the expectation value. So what happens here? We have 1/2 times we're just going to do simple multiplication. So the UD gives 1. The UD/du gives 0. The du/ud gives -0. And the UD/du minus, so minus du/du gives -1. Which gives us what? 0, right? So basically, a normalized state has overlap 1 with itself. So UD with UD gives 1, and DU with DU gives 1, but UD and DU are different orthogonal states, so those cross terms give 0. And because this last bra originally had a minus sign in front of it, the last one enters as -1, so we get 0, okay? That's exactly what we predicted earlier from the probabilities. So what about subsystem B, right? So the calculation for particle B follows in the exact same way. There's no really need to do it again. So this time identity would act on A, leaving A unchanged, while sigma acts on B. So these they would both equal 0. So what have we actually proven? What does this actually mean? What this means is that each subsystem has 0 local spin expectation in every direction. If we only look at A, its outcomes are locally random. +1 or -1, one with equal probability. If we only look at B, it's the same thing. But here's the interesting part. The singlet state is entangled, so zero local expectation does not mean the two particles are uncorrelated. For the special case, so if they were the same direction, let's say they have, but here is what's very interesting. The singlet state is untangled, so zero local expectation does not mean the two particles are uncorrelated. So if A equals +1 and B equals -1, or A equals -1 and B equals +1, +1 equals -1, then -1 +1 also equals -1. Therefore, A expectation value equals 0, B expectation value equals 0, and then expectation value of AB equals -1. So this is true for when A and B are measured along the same direction. So what we're seeing here is individually, I cannot predict what outcome Alice will get. Also, individually, I cannot predict what outcome Bob will get. But if they measure along the same direction, I can predict the relationship. Their outcomes will be opposite. So neither particle individually tells us which outcome we'll get, but the pair can still have a precisely defined correlation. The information shows up in the relationship. And that's the idea about the Bell inequalities and the CHSH. Each subsystem has zero local spin rotation in every direction. So thank you for watching. Appreciate it.